Okay, everyone, so I just want to first show you what's due, what's coming up. So tonight is the homework 1, and Thursday night's the homework 2, and that's on experimental design, chapters 1 and 2 that we did last week. So if you weren't here last week, please review those videos before you try to do these. I also, now what we're going to lecture on today, right here, this is today, we're going to lecture on chapters 3 and 4, and that homework is posted now and due a week from today. And I've opened up this one as well on chapters 5 and 6. Also, this bonus survey that's fun to do, it just will take you 2 minutes, and it'll make analyzing our data more interesting. That's due Sunday. So everything due is at 11:59. That's posted now. So we're going to be using our own data as examples. So I strongly recommend that everybody does that. Now, I can't see your answers. I just can't stress this strongly enough. These are anonymous surveys. So answer honestly, because it will be so much more fun to look at true data rather than fake stuff. And you know what? Lots of times the truth, I think it's more interesting, but lots of times it's even stranger than fiction. So please answer honestly. I just know whether you submit it, not who submitted what. And also these pre-lectures on the stuff we're doing this week are also due on Sunday. Okay, so now you're probably interested in when this R stuff is going to happen, learning the statistical programming language R. I just wanted to first wait until the 3rd week to start that. And so this is this first one, they're all due on Fridays, and assignments 1 and 2 are due on Friday the 7th. So any questions on any of that? All those are assignments, by the way. You're going to be taught through the assignments. They'll have links to videos. I'm not going to lecture on R in class. And one more thing I want to mention here is just remind everybody that these office hours right here are started this week, and everybody's welcome to come. 2 to 5. They'll be different. I'll be there usually Tuesdays and Thursdays from about 3 to 5. But there always will be the instructors for all the courses, all the instructors that teach all these, all of us will be, I'll post the schedule when it's all finalized of who's there when, so you can adjust yourself to find who you want. There's also going to be undergrad TAs there who've taken this course before, and sometimes they might be of more help than someone like me or the other instructors. So I strongly recommend you go there and find somebody who suits your learning style, and I'll post a schedule when that's arranged of who's going to be there when. So any questions before we start? Okay, so let's go to the document camera and begin. Okay, so I just wanted to go over this summary. All the summaries, by the way, at the end of the chapters obviously summarize the important things in the chapters. So I want you to read them. They're important. Now, what did we do? We said, just to review last week, this was on observational studies, and we saw they're not as reliable as randomized experiments for sure. And because why? Because there's differences, systematic differences between the treatment and the control group. The researcher didn't randomly assign them to those treatments, so there's going to be systematic differences. So how do we, and so that means they're likely to have confounders, all right? So why don't we just summarize at the bottom? That might be more useful to you. So let's just go down here. and say what's the basic differences between the observational studies, where the researcher has no power over who goes into treatment and control, they just observe, and the experiments, and the best time where the researcher can choose, and we saw the best way to choose is by randomization. So let's look at these two differences. Okay? That's what we focused on. And the main difference is in the observational study, the treatment and the control group start off unbalanced. They start off different, systematically different. Okay? There's bias. The scales are unbalanced. Whereas in randomized control, the treatment and the control group are without systematic differences. They might have accidental random differences, they will, but those average out with a large enough sample size. So treatment and color without systematic differences. If you want to think of the scale picture, these are balanced groups, and these are unbalanced. All right, so now what about confounders? I know it's confusing. Confounders are confusers. So observational studies are going to have confounders. Differences between the treatment and the control group, they start off different, these differences that get mixed in with the treatment. So they start off different, you give them the treatment, and then you look at the response, and if the response is different, you can't tell whether it was due to the treatment or due to these systematic differences. That's a big problem. Whereas with randomized experiments, as long as they're large enough, there are no confounders. Now, there could be accidental differences, right? But those average out with the big enough sample sizes. Now, what do we do? For the confounder, when there's a confounder, what do? They start off different, so we divide into subgroups, we stratify, and that's, where is it? Stratification, way up here. That helps remove confounding in observational studies by comparing subgroups, okay? So subgroup stratification help what? Make treatment and control more alike. Now, there's no confounders here. We might block, if it's a small sample, on what we think could be a confounder, on what we think could be a problem in getting accidental differences, so we would block first. But the final assignment is random. And after the randomization, we don't want to, so after randomization, we never want to compare subgroups because that will introduce bias. So after randomization, subgroups, like adherers versus adherers, non-adherers, like adherers versus non-adherers, or even adherers versus adherers, subgroups will introduce bias and break the randomization. It will mess up your balance because those groups chose themselves. Any subgroups that choose themselves or happen because of the treatment is going to introduce bias and break the randomization. You don't want to do that. Break the randomization. You don't want to do that, okay? So, it's fine if you block first. That's fine. You can block first is fine, but don't, after the randomization, don't. After they're assigned to treatment and control, don't break into subgroups, okay? And so here, you break into the subgroups and compare subgroups, right? That's what we do with the stratification here. And then we trust the results of the subgroups, and you don't trust the overall results. So don't trust. This was a little bit confusing. Don't trust the overall results, like in Simpson's paradox. Right? That was like Simpson's paradox was an example of that. That you have to break into subgroups. Whereas here, you want to trust the overall results. Because it started off good. So that's why that intent to treat analysis is done in medical studies when people drop out after they're randomly assigned to a drug or placebo. We don't want to just compare the people who stayed in the study. We don't want, even though it's very tempting to do that, to compare the people who faithfully took the medicine in the treatment group to those who faithfully took the placebo in the control group. You'd think, oh, you want to do that. You might want to look at that, but it's very possible that the motivations for dropping out are different in the two groups. Let's say the treatment group, the drug had some bad side effects. People are going to be dropping out more for that, and that won't happen in the placebo group. So you introduce bias. So you want to stick to everyone who started with the experiment, compare them to everyone who finished in the two groups. That was the idea of what we did last time, and that you have some homework questions to illustrate that. All right, so now let's start our next chapter on, and this is not only a next chapter, it's a next whole section on descriptive statistics. Okay, and what this is going to be on is measures of center and spread. All right, so we have a bunch of data, and we want a way to summarize it. We're going to be first looking at these numerical summaries, and then in the next chapter, we'll look at graphical summaries. So with these numerical summaries, there's two basic features of the data that we want to summarize: the center and the spread. So let's focus on the center first. So we have these basic three statistics, measurements of the center of the distribution. The mean, which is just the average. I think you know it's called the mean. It's exactly the same as the average. This is just the average. There's no difference. The median, the middle number. Median is middle. And the mode, which is the most common number. And those are on the list. And those are three different measures of the center. The mean and the median are used the most. The mode is rarely going to be talked about, okay? So the mean, also called the average. Okay, now I introduce some notation in here. So let's go back up to here. And there's a big distinction in statistics. Once you reach inferential statistics, when you have a sample, and you're going to infer something about a population. But right now we're doing descriptive statistics, so this distinction I'm about to talk about is not so important, but just to explain the notation, we might as well explain it here. So there's numerical parameters are numerical facts about the population, the whole population. Okay? And statistics are estimates of those parameters from a sample, usually randomly, but not always, chosen from a population. So, and when you're talking about the whole population, you use these Greek letters. That's where this mu comes in, the Greek letter for mean. You use those because it's an idealized, the whole population, whereas the sample, you use a Roman letters, the letters we're used to, and like X bar is what we would use for the mean of the sample. Now this is going to be important when we go to inferential statistics, but right now in descriptive statistics, we're not talking about randomly, estimating population parameters from sample statistics. We're just talking about you have a bunch of data and you want to summarize it. So let's say we just have the whole population. So we're not going to, so this distinction isn't really important now, okay? So let's just say this is just the whole list of numbers that we have, and we just want a way to summarize them. So you can imagine you have the whole population. This is it, okay? So to find the average, you know how to do it. You just sum up all the numbers and divide by however many there are. And this is it in more formal notation. It just says the mean is equal to, this is a summation sign, so you sum them up from 1 to, we have 7 numbers here. All these 7 numbers, you sum them up and divide by however many there are, 7. So let's just do this now. So we just add them all up. 0 plus 0 plus 0 plus 1 plus 2 plus -5 plus -5. That's -7 is the sum over 7. So we get -1. And that's the average, or the mean. Now, the median is, what is the median? Median, M and D, it's middle. It's the middle number. So to find the median, what you do is you would take these numbers and find the middle number. And don't just take them as given and think, oh, the middle number is 1. No, what you need to do is list the numbers. Your first step is to list the numbers in order, from the smallest to the largest. And then you take the middle number. Okay? Then you find the middle number. So be sure to do that. So you list them from the smallest, that's -5, -5, then the 3 zeros, then the 1, and then the 2. So now the middle number is right here. So the median is equal to 0. Okay, so now there is a middle number if you have an odd. When you have an odd number of numbers on the list, there's a middle number. But what if you have an even number, like here? I've already put them in order. Well, you want to go right in between the 2 middle numbers. So if you have an even number of data points, like here, to find it, you just take the average of the 2 middle numbers. So the median here is just 6 plus 10 over 2. So that would be 8. Okay. So now the mode, what is the mode? The mode is just the most common number, the most repeated number. There doesn't have to be necessarily one mode. There could be 2 modes. In this case, there's just one mode, and it's 0 because it's the most commonly repeated number. So our mode is 0. So that's the idea. Any questions so far? All right, so let's just move on. And now there's these properties of the average and the median. And let's look at these properties. And I think they're very commonsensical. And the first one is that if you add the same number to all the numbers on the list, if a constant is added or subtracted to every number on the list, then what's going to happen to the new mean, median, and mode? You're just going to add or subtract that constant to the original one. And sometimes it's best to just understand it through an easy example. So let's just do that. I think you understand. So let's just do a super easy list. So we'll just do this list just to give you an idea of why this is so. So the list is 1, 2, and 3. So we just have those three numbers. So let's say, so then when you add a constant, let's just say we add 10 to every number on the list. We add 10, and then what do we get? Then we're going to get 11, 12, and 13. Okay, so now you can see here first we can do the median. The median's just this middle number. So our original median is 2. And you can see that our median now is just 10 more. It's 12. So our median is just equal to our original median of 2 plus 10 more, which is 12. So that's what we're doing. So if you add 10 to every number, then the median and the average gets added by 10. Oh, we haven't done the average yet. Okay, so let's do the mean. The mean happens to also be 2 because it's a symmetrical distribution, so you can see that the mean also gets shifted up by 10. So here's your original mean plus 10 more, and so that's 12. So when you add 10 to every number on the list, you add 10 to median and mode. Okay, not median and mode. Median and mode too, but we're not that interested in it. Let's just say median and mean. Okay, the mode would be the same too. So what happens if you multiply each number by, so we'll do the same list, 1, 2, and 3, and now we're going to multiply. So what do we get? We then get 10 multiplied by 10. And we get 10, 20, and 30, and you can see that the median is just the original median, 2 multiplied by 10, which is 20, and same with the mean. So both the median and the mean are multiplied, get multiplied by 10. All right, let me zoom out a little bit. But here's where they're different. The mean is sensitive to extreme values. This is really important. And the median is not, right? I mean, the median's a middle number. So if this number, 1, 2, 3 is the median, but if this 3 was 300 or 3 million, it wouldn't have, the median would still be the middle number of 2, where obviously the mean, the average, would be affected. Okay, so let's just do that. See what happens to the mean and median if you add, let's just do a bigger number, 300, to the largest number on the list. All right, so we'll just do 1, 2, and 3. And now what are we going to do? We're just going to add 300 to the largest number only, to this one. So then we get what? 1, 2, and 303. And you can see that the median doesn't change. But what happens to the average? What happens to the mean? The mean is going to increase, right? You're going to take your original mean, plus if you added 300, if you change this to 303, the sum would go up by 300. So the sum would go up by 300, which means the average would go up by 300 divided by 3. So it would go up by 100. So here the median would stay same, but the mean increases by what? We added 300, so it would be 300 divided by 3. If we added 400, it would be 400 divided by 3, etc. Okay, any questions on that? So now we're going to look at numerical summaries of the spread of the distribution. So if I just tell you the average, like if I just say to you, oh, the average in our exam last semester was 80. That gives you some information. If I said the median was 80, that would give you information too. But what you want to know is what the spread around that is. What the spread, does that mean that everybody got very close to 80? Like everybody got between 75 and 85? Or that means something very different than the scores ranged all the way from maybe 0 all the way up to 100. So you want to know what the spread is, and that's the various ways to summarize the spread of a list of numbers. So here's the range is the simplest way. The range is just the spread from the smallest number to the biggest number. It's the simplest measure of the spread, and it's just the difference between the smallest number to the biggest number. So here, what would the range be? The range would be from the biggest number to the smallest number. So the largest number minus the smallest number. It's always expressed as positive number. So it's 2 is the largest number minus the smallest number, and so the range is 7. It's just the distance between the smallest number and the largest number. Okay? That's really easy. But what that doesn't capture anything, but imagine like the smallest exam score was 0 and the largest was 100, but let's say everyone else was really clustered around that 80. That would be very different than if there was a spread. You want to see how all the numbers are spread out from the average, not just the largest and the smallest. So that's what the standard deviation does. What it sounds like. It's the typical deviation the numbers are from the average. So it measures the typical deviation or typical size. Range is the wrong word. Typical size of the deviations from the average. All right? So think of it as it's like the average distance. All the numbers are from the mean. It's not exactly that. We'll calculate it on the next page, and you'll see what it is and why. And then the variance is just the standard deviation squared. And we'll be talking a lot about the variance later on. But first, let's just see how they're calculated. So let's turn the page here. Okay, so I'm sure this is review for a lot of you, but we might as well go through it. Okay, so here's a graphical display of how these numbers, look, you can see these numbers, they're centered at 0, and there's lots of numbers very clustered around 0 here, and here they're a little bit more spread out from 0. They have about the same range. In both pictures, they go from -6 to 6. Well, they actually go further, but in the picture, from -6 to 6, so the range is about the same. But which one do you think has the larger standard deviation, and why? So do you see that these numbers, you want to see the standard deviation measures the typical spread, how the typical size of how far they are from the average. So you can see the average and the median is both 0 here. And do you see how there's more numbers further spread out? They're all bunched around 0 here. So the answer would be this one. We haven't really talked about histograms yet. That's what these are, but we will in about 10 minutes. So because the numbers are more spread out. Okay, so standard deviation is really basic, a simple idea, but the calculation is complicated, and so many people get confused by what a standard deviation is, especially if they just learn it symbolically. So I wanted to put the words here too. I hope that will help. And I think I want everybody to know how to, by hand, take a standard deviation of a simple list of numbers, because it's important for you to understand what a standard deviation is. It's the basic, it's one of the base variations, the basic, how things vary is the basic idea behind all of statistics. So if you don't know what our measurement of variation is, variance and standard deviation, you'll really be at a deficit. So I want you to get a good picture of it, an intuitive idea, and sometimes it's just by doing calculations a bunch. So I want you to know how to do this, in other words. I know how to do this. Okay, so the standard deviation is sigma as in the population, you'll see that, or S for the sample, or a standard deviation is how I'm abbreviating it. All right, so here it is in symbols. Let's just go through it. So what do? We first find the average of the list. So here's a simple list, and you just want to find the average. So let's do that first. If you want to find the deviations around the average, you have to find the average first. So what's our average? So the average, just add all those numbers up, and you get 21, and there's 7 of them. So our average is 3. I bet you could see that because it's symmetrical, and 3 is right in the middle. All right, so that's our first step. And now our second step is to subtract the average from each number. That's what a deviation is, okay? Subtracting the average from each number. So let's get those deviations. You can think of it as the value minus the average. Okay, so let's do that for each one. Our average is 3. So our first deviation is going to be value minus 0 minus 3. That's negative 3. 1 minus 3, negative 2. 2 minus 3, negative 1. Now 3 is right at the average, 3 minus 3. So this has no deviation from the average. It's the average. Now this is 1 above the average, 4 is 1 above. So 4 minus 3, that's why it's a positive deviation, because it's above the average. 5 minus 3 is 2, and 6 minus 3 is 3. So note, if it's above the average, it has a positive deviation. If it's below the average, it has a negative deviation. So those are our deviations. Now, you'd think now you want the typical deviation, so why not just take the average of all those deviations? Why not do that? Well, look what happens when you take the average. You add them all up, and we divide by however many there are, which are 7. So you add them all up, and look what happens. What do you get? 0. So, and you will always get 0. In fact, we should write that the deviations, and let's write it right here, they always sum to 0, which means their average will always be 0. So we can't do that. All right? You might think, well, why don't we just take the average of the absolute values, the average neglecting sign? And that is done, and that is what some people do, but not generally speaking. If you did that, you'd get something just a little bit less than what we're going to do. You'd get what? 14 divided by 7. So it would be a little bit less than what we're going to get. So what do we do instead to get rid of the sign? We don't take these absolute value. What we do is we square every one of these numbers. So those are the deviations squared. And this is why it's much more complicated. So I want you to think of it as just the average of these numbers. If you want to estimate a standard deviation, just think of the deviations and take the average. But the reason we don't do that is basically because that absolute value function is not very easy to work with, and this squaring function is much more, deviation squared is much an easier function to work with. So it's basically just for that reason. So you take the deviation squared, and when we do that, you see the signs disappear. -3 squared, -2 squared, -1 squared, 0 squared, 1 squared, 2 squared, and 3 squared. So that's what we get. And now, but now we're in squared units, so if we want to, first let's take the average of these squared units, and that's what's called the variance. We're right here, the average of the squares. This is called the variance, and this is a very handy statistic to work with. So the variance, you'll see all the time, it's the sum of the square deviations divided by how many there are. So let's do that. So that's all divided by 7. 28 divided by 7, and we get 4. So that's what's known as the variance. But this is not in the units of the numbers. So for example, like let's say these were the number of brothers and sisters people had in the class or something, you could say, oh, the average is 3, and give or take what? Well, you wouldn't say give or take 4 squared brothers or sisters. It's in a different unit, so we want to take the square root of that to get it back in the units of our original number, and that's the standard deviation. So that would be the standard deviation would be equal to the square root of 4, which is 2. So how does that compare to if we just took the average of these, neglecting sign? So we can look at that. Note, the SD is always just is just slightly bigger than what? It's slightly bigger than the average of the absolute value of the deviations. When I mean it's like, which would be what? If we did that, it would be 3 plus 2 plus 1 plus 0 plus 1 plus 2 plus 3 over 7, right? And that would be about 1.7. Actually, it's that. So 2 is our standard deviation, and it's always just a little bit bigger than 12 sevenths, 1 5/7. Any question on that? All right, so now, let's look at let's do the same thing with the spread, with the standard deviation that we did with the average. So what happens, we saw when you add the same number, it doesn't, the average increases by that much. What happens to the standard deviation? So if you add or subtract the same constants to every single number on the list, the standard deviation doesn't change. Why? Should I just do this quick example like this? Why wouldn't it change? Let's think about it. So if you, so you have the list, 0, 1, 2, 3, 4, 5, and 6. And if we add 10, so we'll add 10 to each number. And then we get what? 10, 11, 12, 13, 14, 15, and 16. And can you see how the spread is exactly the same? The average goes up from 3 to 13, but our deviations are going to be the same. If we subtracted off our value minus the average, you'd get 10 minus 13, -3, -2, -1, 13 minus 13, 0. We'd get these same deviations, so the standard deviation would be the same. So that, in other words, graphically, you could just see it. You're just taking these numbers and shifting them. You're not changing the spread around the average. So the deviations are the same, the spread is the same. Deviations don't change. Spread doesn't change. So standard deviation and variance doesn't change. Okay, that makes sense. But what if you multiply or divide all the numbers? Then the spread is gonna, let's see how that looks. So let's do the same thing. 0, 1, 2, 3, 4, 5, and 6. And now we're going to multiply each number by 2, let's say. So we'll multiply each number by 2. So let's try to draw it to scale, all right? So 0 times 2, that's 0. Now 1 times 2 is going to get more spread out. See, 2. 2 times 2, 4. There's going to be distances of 2 between every number. 6, 8, 10, and 12. You can see the range doubles. The standard deviation doubles. You can see the deviations now. The average doubled, and each deviation from the average is now doubled. So the spread doubles, and the standard deviation doubles. The spread doubles, the deviations double, so the standard deviation doubles. Okay? Now what do I say here? Okay, say if you multiply or divide every number in the list would be by the absolute value. Okay, so let's try -2. What do I mean by that? What if I multiplied by -2? What would happen? You'd get 0 times -2, 0. But 1 times -2 is negative. 1 times -2 would give us -2. So it would be -2. Then we'd get -4. We'd go all the way up to -12. So they'd get spread out just as much. Now, can a standard deviation ever be negative? If you did the math, it wouldn't be. But what does it even mean to have a negative deviation? We're taking, the standard deviation can never be negative. It just describes the size. If you think of this calculation of how we do it, it can't be because we're squaring these deviations always. So it can never be negative. Does that make sense? Okay. By the way, can it ever be 0? Can the standard deviation ever be 0? What do you think? When would it be 0? Go ahead. If all the numbers on the list are the same, yes. If all the numbers were the same, like if they're all 3, then all the deviations would be 0. They don't all have to be 0. That's one case of it. But if all the numbers are the same, that means there's no spread. Like if everybody scored an 80 on the exam, every single person, then the standard deviation, the average would be 80 and the standard deviation would be 0. Okay? Now, if you multiply or divide every number on the list by the same constant, okay, the variance would be multiplied or divided by that constant squared. Well, the standard deviations double, so the variance would be multiplied by that constant squared. For example, in this case, it would be multiplied by 4. If you multiplied it by 6, every number by 6, then the standard deviation would get multiplied by 6, but the variance would get multiplied by 6 squared. All right, now I'm talking about variance because it has this very important property where the sum of the variance is the variance of the sum. So that's why it's used so often, why it's very, very handy. why we do this. It's one reason we do these sum of squares and instead of taking the absolute value. So, and people work with variance instead of standard deviation all the time because they add and standard deviations don't. We're going to get it. This is if they're independent. We're going to talk a lot about this later, but if you're interested now, you can, because I know some of you have had this stuff before, you can see the proof of this. I tried to make it pretty intuitive proof on page 228. But we're going to talk about this later on a lot. We haven't even talked about independence yet, so it's to come. All right, now let's see what we're going to do next. Summary. All right, good. Now, again, I can't emphasize enough, especially when you're studying for an exam, just read over these summaries. All right? They're all really important. Certainly that you should keep in mind that extreme values have a strong effect on the average. And the average moves towards the extreme values, as we saw. This is especially important in things like when you're looking at average income, because there's some, it's some very extreme values, billionaires, right? And so they're going to raise the average. Sometimes what you're more interested in is actually the middle income and not the average income, because the average income, for example, in this country will always be much bigger. So if somebody promises that you're, this is, says the average income is such and such, and you think, oh, great, that's pretty wealthy. You have to remember that's different than the median, which is always lower. If you have extreme big values, if you have extreme small values, like on our exam data, where some people get zeros, a lot of people get around 80s and 90s, and some people who don't show up or are clueless get really low scores, and that always drags the average down. And our median is always higher than our average on every exam I've given. So it depends on your data set. So we're going to be looking at that a lot. All right, let's see. What's this say? The standard deviation measures the typical spread of the deviations. Okay, we saw it's usually just a little bigger than the average, neglecting sign. The standard deviation is calculated by taking the root mean square of the deviations. This is going to come up a lot, this root mean square. As we move into more sophisticated data analysis, we'll see this a lot. So maybe I'll just explain it because it will help you remember it later. So what are we doing here? In these steps, the last step is we're taking the square root of the mean. So here you can think of it, this is the square root, which is the root of the mean. The average is the mean of the squares, root mean square of the deviations. So that's it. That's what it means, root mean square. You'll see that a lot. It's an easy way to remember the steps. All right, and now the standard deviation is never negative. This is super important, of course. And this is what we talked about. When the same value is added or subtracted to all the numbers on the list, the average increases or decreases, but the standard deviation remains the same. It just gets shifted. The shape is the same, but when all the numbers are multiplied or divided by the same value, both the average and the standard deviation are multiplied or divided by that same value, unless, of course, it's negative. Okay, I think that's good. Now let's go on to the next chapter, which is graphical display, graphical summaries of the data. So I said the first was numerical, and now we're going to look at ways to graphically display the data, mostly with a histogram. You're awful quiet. Anybody have any questions before we start this chapter? Okay. Let's do it then. So, the main graphical display of the data you'll see in this class and in most of statistics is something called a histogram. And we're looking and it's a way to graphically display numerical data. Okay, numerical data, not categorical data. Data that can be characterized described with a number, not a category. Like your height is a numerical data, your favorite color is a category. So histograms, this x-axis right here is drawn to scale. It's not just categories, these numbers have meaning and they're drawn to scale. And the histogram uses, so here, let me say, let's first, so it's quantitative. So if we have numerical data, this is a good way, not if you have categorical data. And we use areas to depict the percentage of the data that falls within any interval here. So, the width of these intervals indicates the size. For example, this is a histogram of final exam scores. So this right here are the people represent the data that's scored between 0 and 50 on an exam. And the area of this block represents the area of this compared to the whole thing. The whole thing, in the histograms we're looking at, we're going to say the whole thing is 100%. So you think, what percent of the area? What is this block of the whole thing? You know, it's less than half. It looks like about what? A third, a quarter, something like that. So the area of the block represents the percentage of the data that lies within this interval. And this axis right here is the density, which says it describes how crowded each interval is. This data is spread out, so it has a low density compared to this one. This one has the highest density, the most crowded interval here. All right, so so I say histograms are also known as, if they add up to 100%, like the ones we're looking at, in a histogram, the ones we're looking at. Some other people look at histograms that don't, but the ones we're going to be looking at all add up to 100% because it's getting you ready for higher statistics classes and where these probability density functions feature in very heavily. And histograms, the description of the histogram, there's a description of them. As long as they add up to 100%, it's known as a probability density function. And this density is the label for the y-axis. So sometimes you won't even see this y-axis. I say it can be changed because if you know that the whole histogram adds up to 100%, and you know the percentages of the blocks, and you know the widths here, the density can be determined. Also, you can change the density without the scale you can change without changing the shape of the histogram. Right now I have it as percent per point. Like between 0 and 50, there's 50 points. But I could, for example, we could change it to percent per half point. Then there'd be 100 half points in this interval. And then you would just make this be, you change the scale. You just divide these by 2. That doesn't really matter that much. Let's look at figure out the percents here. Okay? What percent of the students scored between 80 and 90? Let's look at that. So how would you know that? What percent scored between 80 and 90? Well, that's an interval 10 wide there. That's 10 points. And what we want is just the area of that rectangle. So that's width times height. So it would be, in this case, the width is 10 points times, well, we have to get the height. I'm sorry, I didn't really make it clear here. If you go across here, this should be 2.5 per point. Let's fill them all in. This is 0.5% per point. That's what the label for all of them is. These are both 1. This one's 2, and this one is 1. And I'll do that on your homework or on your exam because it's kind of hard to read what those are. Okay, so now we can do the problem. It says what percent of the students scored between 0 to 80 to 90. That's 10 points times 2% per point. And you see the points cancel out, and we get 20%. That's the answer. Why don't we do them all? Let's do them all. So we know that this is 20%. What's this one? That's 10 times 1, 10%. And these are all 10 times 1, so this is 10%. See, they're the same. This one is 10 times 2.5, so that's 25%. And what's this one? 50 times a half, so that's 50%. Any questions on that? And now make sure that they all add up to what? Make sure they all add up to 100. And do they? I did this wrong. Duh, no wonder everybody's, what did I do? What's half of 50? Half of 50. 25. I didn't do that on purpose, just to see if you're on your toes. Actually, what I was thinking, well, you don't need to know, I'll just confuse you. All right, so now, and we should have seen that. You know what it says when it's 25? It says that this block is the same area as that block. Does it look like it? It's sort of an this one, would you have guessed this block, the area of that, is equal to that? It looks about the same, right? So I could see some people were, it's the first rise I got out of you. I should deliberately make mistakes to see if you're asleep or not. It was like I saw some people talking, wondering. It was exciting. All right. Now, thank you so much. All right, and now we didn't do this question. What percent scored exactly 83? So if you don't, exactly 83. Well, 83 would just be an interval of 1. Here, you could say from 82.5 to 83.5. It's just an interval of 1. And so it would be 1 times 2, so it would be 2% per point. Let's say you have to assume an even distribution for each interval in order to answer that question. Like, I'm assuming that the people who scored, the same percentage of people scored 81, 82, 80. It's a big assumption, but let's just assume that. Now, if not told otherwise, assume that. All right, so let's do that. It's 2%. Interval of 1 times 2. It's the same as the height of the interval. And that's what the interval is that's what this is telling you. What percent scored for each point? So 2% for 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, and that's the 10 times 2. Now, let's move to the next one. To drawing and reading histograms. Okay. Now, if you were in Stat 100, this is really familiar because these notes so far are pretty similar. Little differences, but pretty much the same. So you've already done this example. Now, the table below gives the GPAs for a high school senior class of 500 people. So there must be 500 students here. They all add up, and there are, so that's 500 students. Now, so this is this table here that tells us how many are in each one of these intervals here. So if we're going to draw it, the intervals go from 0 all the way up to 4, the GPA. So it's 0, 0.5, 1, 1.5, 2, 2.53, and 3.5, and 4. Those are the GPAs. Okay, now, so we're told the width of these intervals, like the first interval is between 0 and 2. but we're not given the height. That's what we're going to figure out here. It's going to be the height. But we are told the area. The area. And we are told the width. So we know that the height is area divided by width. So we're not really told, how can we get the area here? Well, area, remember, is the percent of the data within any interval. So 50 out of 500 is what percent? 50 divided by 500. So that means that 10% of the data is right there. Okay? So let's do them all. So now 150 out of 500 is 30%. 250 out of 500 is 50%. And 50 out of 500 is 10%. Now, I better check myself because I don't want to make a mistake again. What is that? Does that add up? Yes. Good. It has to add to 100. Now, we know the width of the interval. If we're saying it's 1 point, you know, how many points are there? So that's 2 points. That's 0.5 points. That's 1 point. And that's 0.5 point wide. All right. These are all points. All right. And now to get the height, area, height times width is area. So height is area divided by width. So all we have to do is do the division. So for this one, it's 10% divided by 2 points is equal to 5% per point. So there's our density, percent per point. And the next one is 30% divided by 0.5 points. So that's 60% per point. And the next one is 50% divided by 1 point. That's easy. 50% per point. And the last one is 10 divided by 0.5, which is 20% per point. Okay, so that's this density scale here, right here. And it goes all the way from 0 to 60. All right, so this would be 10, 20, 30, 40, 50, and 60% per point. That's what that is. So now we can draw the histogram. So for the first one, it goes from 0 to 2, and it goes up. The height is 5. So here's 10, so 5's there. So it's got to look like this all the way to 2. All right. And then the next one goes from 2 to 2.5. It's a smaller one. And how it goes all the way, whoa, that's the tall one. It goes all the way up to 60. I'm going to put this over 0.5, and this is 60. The next one is 1 unit, and it goes as high as 50. So that's here. So that's 50. And the last one is just a half a unit, and it goes to 20. So it's there. So let's make sure we did this right. 2 times 0.5 is 10%. And that does match up. We want to get these numbers. So here we have 2. There's a half of 60 should be 30% of the data is here. That's 1 times 50 is 50% of the data is here. And lastly, a half of 20 is 10%. So these are the same area. 1, 2, 3, 4 blocks here. Yeah, 1, 2, 3, 4 blocks here. Yeah, so these are the same percentages. And this by far has the most. All right, so that's the idea. The interval has the most people. Is it the tallest? No, it's not the tallest. This one's the tallest. Does it have the greatest area? Yes. How about this? If you added 1 point to everyone's GPA, how would the histogram change? Let's say GPAs could go up to 5. So if they went up to 5, how would the average change? Let's think about it. So if you added 1 point to everyone's average, the average would what? Would it stay the same? No. What would it do? It would go up by what? 1. If you add 1 point to every single person, and the average is going to go up by 1. How about the standard deviation? Would that change? No, because the spread, the histogram would just shift. The whole histogram would just shift up to 5, 1 point. It would be the same exact thing. We could just redraw the scale. If we change these numbers from 1 to 5, and we'd have the same histogram. Okay, so no, the shape would stay the same. All right, last question on this page. If you added 1 point only to those in the 0, 2 block, how would the average and standard deviation change? Well, the average is easy because if you add, what would happen to the average? I'm not asking for the exact numbers. I'm just saying, would it go up, down, or stay the same? It would go up because even if you just make one person go up, the average is going to go up because the sum will go up. So the average would increase. Now, what would happen to the standard deviation? The picture really helps. Think about it. If you add 1 point to just these people and leave everybody the same, so what would happen to this block? 0 would get shifted to 1. So the range would go from 0 to 4. These people would get shifted up 1. What would happen? So what do you think? If the range is this part going to increase? No. This part, if you add everybody 1 point, do you see how the spread's going to decrease? Does that make sense? Does everybody see that? So the standard deviation is going to decrease, right? Okay. Standard deviation would decrease. Oh, shoot, I did this last time, and I don't know what I did. I'm really sorry. I got to wash my hands here. Watch them. I don't know why that happens. It must be I'm touching something down here. So I think we'll get it back again. I'm very sorry this happened again. Come on. There it goes. Yeah, it's very sensitive. Come on. Focus. Okay, so the SD would decrease because the spread decreases. Oh my goodness, am I going that slow? All right. So all right, so let's think about, so here these are these smoothed out histograms, right? And let's think about where the mean and the median is on these histograms, okay? So the median divides the histogram exactly in half. It's the middle number. So think of it, the middle number, 50% is on one side, 50% is on the other side. So that 50% of the data. So that means 50% of the area is on one side and 50% on the other. That's the median. But the histogram is where the average, is where the histogram balances. So if you think of like a seesaw, like a fulcrum of the seesaw, if the data goes farther out, the average goes up. If the average is going to move towards the extreme values. So let's just think about this. Let's look at this one. So here you see, in a symmetrical distribution, the average and the median are the same, right? So that's easy. But how about if you have this long right-hand tail? The median's going to be like someplace where if you drew a vertical line that divided this histogram into two equal pieces by area, that would be the median. I just want to know where the average would be in relation to that median. Do you see how big values, extreme values far away from the middle, are going to increase the average compared to the median? So here, do you see how the average is going to be greater than the median? Think about like if this was income, the average would be, there's a big tail here. So the average is greater than the median. Whereas this is more like our exam scores, where the average is less than the median. These extreme low scores drive the average down. So here, long right-hand tail, greater, long left-hand tail, less. Any questions on that? We'll look at this a lot more with our actual data when later on. Now, types of variables. Okay, so we saw that that the histogram is only relevant for quantitative data. So the key distinction is between quantitative and categorical or qualitative data. Okay, so quantitative data are best described with histograms, can be displayed using a histogram, whereas qualitative data that's not described numerically, like any question you'd answer with a category instead of a number, like what's your favorite movie star, or what type of movies do you like to go to, what's your favorite color, what sex are you, race are you, country you're from, any of that stuff is going to be best described with a bar graph, where the horizontal axis has no quantitative meaning. It's just a category name. All right, so then you take quantitative data, and they can either be divided into continuous or discrete. And continuous data is data like time, temperature, height, weight, where between any 2 points, you could have an infinite number of points. You could break it down smaller and smaller and smaller. It's continuous. So it's things like time, temperature, height, weight, etc. And the idea is it's continuous between any 2 points. There are an infinite number of points. You can make it smaller and smaller divisions. And discrete data is that is countable, like the number of brothers and like family size. There's discrete units like pulse rate, etc. What else? Number of teeth you have, number of teeth, etc. It's countable. Countable. You can just count how many pulses you have in a minute, etc. All right. So now, of course, boy, that looks. The hour gets on. My handwriting gets worse. Of course, you can round this continuous data, and we usually do. Like your height, you can round it to the nearest tenth, and then you could say it's discrete. Okay? But now, categorical data is data that falls into descriptive categories, and they can't be displayed on a histogram because the categories don't have any numerical meaning. So there are things like color, gender. How about something like zip code? Do you think it's described with a number, but does that number have any meaning? It's not like the zip code refers to how many people or anything that are in a particular zone or the area. So it's just zip code is just a category. It's just using a number to describe a category. Same with, social security number, telephone number, etc. Those are all just categories. Okay, so those are qualitative variables. Now, the last thing is, so what is a variable? I didn't even say. A variable is just a characteristic of, let's say, the data that varies from subject to subject. So that's all it is. A variable varies. Just some characteristic. It's quite easy. And they can be quantitative or qualitative. And of course, you want to read all this. And that's, might as well end there. So we'll start next time on chapter 5. Any questions before we quit? Okay.